Okay, so first we covered asynchronous serial communication. Why do we bother with synchronous serial communication? Well, as you may have noticed, for asynchronous serial communication, to send, let's say, 8 data bits, it took 10 bit times at least, a start bit and a stop bit, for synchronization. That's kind of a pain. That's, depending on how you measure it, 20 or 25% extra time wasted. How about if we can get rid of that? Well, you can if you add a clock, if you add a synchronizing signal, an extra wire. So now instead of the 2 signals plus ground, we're going to have 3 signals at least. And that clock will allow us to do what's called synchronous serial communication, called SPI or SPI. And the S stands for synchronous, and PI is peripheral interface. Okay, and so that's what we're going to do with this lecture, all of today's lecture, and some hardware we'll look at later related to your lab. Okay. And of course, if you have the textbook, a version of the textbook, SPI is covered in great detail, but you got the manuals that covers it as well. Okay, so it stands for Serial Peripheral Interface. It came by Motorola, created it, but everybody uses it now. It's a standard that's used all over. Data can go in both directions at the same time. That's full duplex, and but full duplex with separate wires, just like asynchronous serial, as opposed to I²C, which is a single wire both directions. Okay, and so SPI, lots of hardware devices you could buy connect to microprocessors through SPI, one of which you'll be using in your Lab 6. And when you have SPI, you have this thing called a master and a student. There are 2 SPI systems. One's called the master, the other's called the students. It's not really called the student, but what it's really called is a triggering word, so we try not to use that, although all the manuals will call it that other S word. So master student comes from a lot of places, but one place is The Karate Kid, an old movie from the 80s that was a really good movie when I was your age or a little younger. And then they made a HBO or Netflix series called Cobra Kai, which is still going. It's in the 6th season. And this is Mr. Miyagi, and he's the master, and this is Daniel, the student. Some cute little videos that talk about some things. Anyway, master, student. Master is in charge, student follows. So here I've got a setup of 2 systems connected through SPI. There's potentially 4 signals in SPI, 4 wires, in addition to ground. MOSI, master output, slave input. MISO, master input, student output. And SCK is the serial clock. And SS is student select. Okay. Student select is, I've never seen it anything but active low. And so if you have multiple students, the pin that goes low, that's the student that has been selected. Now, you don't necessarily need to have the student select pin. If you have a master, we can just make that pin an output, and then it's no longer associated with student select. And if you only have one student, then you can make this always ground. And again, this is no longer needs to be a signal, just completely grounded. Okay, so if in the beginning of some process, the master has this information and the student has this information, and then you write some data, well, if you write this data to the data register on the master, after 8 clock times, 8 of these clocks, then the data that used to be in the master is now in the student. Okay, I guess it shows here. The data that used to be in the master is now in the student, and the data that was in the student is now in the master. Okay, so these are the 4 signals used, and the student select could be used if you need to. So a block diagram, just like we did for asynchronous serial. What are all the systems? What are all the controls? How does it work? Well, again, there's 2 pins, MISO and MOSI, and it depends if you're a student or a master, which are which. There's some kind of buffer logic that you can set the data direction for each of these. And again, it depends if it's a student or a master, what the data direction is. Of course, there's got to be a clock source, and it all derives from the system clock, typically. So we can do some divide bys just like we did with asynchronous baud rate stuff. And eventually we get to this clock. And then there's several registers associated with this. There's the shift register, just like asynchronous serial communication. Anything serial always has a shift register. There's a read buffer, and a data register, and some logic that says, well, we'll see some of the things it says. There's always, every system we've seen has status registers and control registers. So you can set it up properly and to know when it's ready or finished or something like that. And of course, if you enable interrupts, there are some interrupt flags that can cause interrupts. So general block diagram, very much like what we had for asynchronous serial. And this is the poor excuse from a block diagram in your XMega manual. It's not great, missing a lot of detail, but again, it shows two shift registers. And it has the word master and it has the word student. The master side, that output goes to the student input. So MOSI goes to MOSI and MISO goes to MISO. So if this is from the student, it sends something out from the student, it goes in to the master. Okay, and it shows that the clock always, remind you, always the clock comes from the master. Again, this doesn't show it very well, but the clock is generated from the master side, not the student side. Okay. So master initiates the operation. Student just waits around till the master's ready to start something. Before the master starts something with the student, if there is multiple students, you got to make that student select pin go low to tell it which student you're talking to. And the data, each clock edge, particular clock edge, triggers the reading of the data from the input device, whatever that input device is, whether it's a student or the master. A particular edge of the clock says, now's the time to read. So you initialize the data transfer by writing to the data register. Just like asynchronous serial communication, you transmit information by writing to a data register. Here, you got to write to the master's data register to initiate the transfer. What if the master is only receiving data, never sending data out? Well, still, it's got to be initiated from the master. So you'll send out junk, whatever garbage you want to send out from the master. Won't go anywhere. Maybe it just, a wire's not even connected. But that is what starts the clock going, which then allows the master to get the inputs from the student. Message link is always 8 bits. I've never seen a microprocessor that had a SPI of other than 8 bits. Now, it doesn't mean that you can't transmit 16 or 24 or other values of bits, but that means multiple SPI sequences, as we'll be using in our lab. Okay, now, unlike asynchronous serial, you can do either most significant to least significant, or as in asynchronous, least significant to most significant bit. Either way, there's a pin in a control register called DORD, data order, that lets you set up either direction. It's in the control register, at least for our processor. So there's sections in the 2 manuals we mostly use that describe this. These are the 4 configuration registers we'll use the most, and we'll go over these now. So first, ports C, D, E, and F, the same ports that had asynchronous serial, had 2 asynchronous serial ports, has 1 synchronous serial port. And you can see they take some of the same pins. So here's the asynchronous serial 0 for port F, it looks like, port F. And here's asynchronous serial 1. Actually, we just use those pins. And notice that this is the synchronous serial, and it uses those same pins. So you obviously can't have both of these run at the same time. I believe there's a way to remap these pins to here, just like we remap the pins in homework 2. Don't quote me on it, but I think there is. You won't need to do that. Okay, so the pins looks like we're using pins 4, 5, 6, and 7 for SPI on each of these ports. Okay, 8 bits. can send data both directions at the same time. The master could, if it has a bunch of students listening, you can select all of them as long as only one student sends back. You can actually have, like in this case, 45 students listening to one master. Okay. The maximum speed this can go is half of the system clock speed, which is much, much faster than asynchronous serial communication. Okay, and that's always the case. SPI could be faster than asynchronous serial. Asynchronous serial requires, sampling, remember, 16 times faster than the actual signal, and that limits the speed things can run. So up to half of the speed of the processor, at least for ours. There's this thing called phase and polarity, which our manuals call mode, which allows you to interface with any SPI system. There are 4 choices of phase and polarity, and this gives you every possibility. And we'll see this in our when we look at the specific figures in our manuals. Again, we can set up data ordering either way, master to most significant to least significant, or least significant to most significant. Unlike asynchronous serial communication, the transmitter is unbuffered. It is not double buffered. In asynchronous, both the transmitter and the receiver are double buffered. Since the transmitter is unbuffered, that means if you want to send something out, you write something to some data register, start sending out. If you immediately write another byte, it'll get overwritten. And that would be there's some kind of error bit that could be set if your particular microprocessor has that. I don't believe ours has that status bit about overrun error. So anyway, so if you overwrite it before the flag is set that says you're done writing, sending the data out, then you're going to lose it. Of course, when the 8 bits are sent out or received, a flag can get set, and that flag can generate an interrupt if necessary. Clock always is going to come out of the master, not the student. Okay. Lots of words. Let's look at some figures. Lots of words. Okay, so here is the mode polarity or the phase polarity possibilities. So this is in the A331 manual, and it shows mode 0 and mode 2. There are 2 things important for this phase polarity or mode. One is, what is the clock value when there's no clock happening? So what's the constant value when there's no data being transmitted or received? And then which edge of the clock is the time for sampling to occur? So I don't know why they organized it this way, but it looks like here for mode 0, low is the default value. For mode 2, high is the default value. And if you look at the sample time, it's the falling edge for mode 2 is when it's sampled, and the rising edge for mode 1 when it's sampled. This is in the center of the bits. We always sample in the center of the bits. So let's look at this again. Low and rising edge for mode 0. Well, let's look at mode 1. Low and falling edge. Let's look at mode 2. High is the default and falling edge. For mode 3, high and rising edge. That's all possibilities. So we have to make sure we set the default value of the clock to the particular low or high that is necessary, and the particular edge that the device we're talking to needs. If you're talking 2 microprocessors, you can set them both to match whatever you want. But if you're talking to one particular device, this device has some requirements. Yes, sir.
What's the point of polarity? Like, what's the practical use of polarity?
To be able to talk to any device. When somebody makes a device, let's say it's a GPS, they have their requirements for that device. If 2 companies make different ones that have different polarities on their for their part, and you want to be able to talk to either with your microprocessor, you better have that control. So why they do this? They could have a standard and everybody does the same, but they don't. And so this allows you, no matter what, the phase and polarity, we can connect them. Okay. Okay, so here's the control register. It's just called control in the SPI section of the manual, but in your include file, it'll be SPI, N is C, D, E, or F, and control is the name of the configuration register. There's this thing called clock times 2, which can give us faster clocks. If clock times 2 is false, then they're half as fast as they would be if clock times 2 is there. Enable will turn on the SPI system like every other system in the XMega. It's off by default. Doored, again, that's for data order. The default is most significant bit first, and a 1 there will make least significant bit first. Master, you have to say it's a master. You put a 1 there, it's a master, and if you put a 0 there, it's a student. Then mode, we have the 4 possibilities, 0, 0, 0, 1, 1, 0, and 1, 1 for mode 0 through 3. And then prescaler allows us 2 bits to control the speed. So if you look at these 2 bits plus this bit, 3 bits to control the speed. So you'd think you'd have 8 speeds. Turns out you only have 7 because you get 64 2 different ways. Don't know why they did it, but they did. And so there's a way to get the clock period divided by 64 with this being a 1 or this being a 0. Anyway. Then there's the interrupt control configuration register. This is where you say, hey, I want an interrupt. And if you want an interrupt, it'll be either 1, 2, 3 or 1, 2, or 3. Low, medium, and high. 0, 0 means no interrupts are going to be used. Then there's the flag, interrupt flag. So that says I've just 8 clock times have happened. Oh, that does have right collision. So right collision would be if it was sending out something in the transmitter, you put something in the transmitter, and before it finishes, you send something else in the transmitter. That's a right collision. So our processor does have it. Okay, that's status. And then data register. Just like the asynchronous serial communication, there are 2 different data registers with the same address. You write to the one for transmit, and you read from the one for receive. Okay, just like it was before. Okay, now that SS pin, the student select pin. If you have a student and you just leave the pin float, you don't tie it to anything. A pin that isn't set to be output or input, what is it going to be on your XMega? I saw your input. And it's input because if it was output and we tied 2 pins together, it would blow up. If it's input and you tie an input to an output, no problem. Input to input, no problem. I mean, it won't blow anything up. And so pins are default input. And what is the value that you'll read at an input pin that's connected to nothing? Who had 3701 with me and heard about magic tricks? Do you remember the magic from logic gates? What the magic would be, you have some kind of AND gate or OR gate or whatever. If you leave one pin unconnected, the other pin tied to a switch, you can make the light, the output's tied to an LED. You put your hand near there, the light goes on. You put your hand away, it goes off, or vice versa. Magic trick. Unconnected inputs, there is no guarantee what they'll be read as. They're not automatically low or high. Now, depending on the technology, if there's nothing nearby, there'll be one value. I'm not sure. Again, it depends on what kind of chips you use, whether it'll be low or high. But in reality, in a circuit board that has a bunch of things near it, it depends what's nearby. That'll influence the pin. So you never leave the student select pin floating. If you're not going to use it, tie it to, if it's a student, tie it to ground. If it could be selected or not selected, what you would do, and we'll see an example of that, we'll put a pull-up resistor to it. So the default for the student select will be high unless we output a low here, and then it'll be low. And we'll see that later. So always just put a pull-up resistor to it or make it always true. Okay. And so again, here I've got an example of a master connected to a student. And if there's only one student, I can just ground that pin, make it always a student. Now for the master side, if you don't need the student select for the master. If you only have one master. And if you have in a system multiple masters, then that means all of the masters have to sometimes be students. And that's much more complicated. But again, you don't want to just leave this thing unconnected. So if you have one master, if you make that an output pin, then you don't have to worry about it ever being low. And if you make it an output pin, then it's just an extra GPIO. You can use it for anything. And we're actually going to do that in our lab. We're going to use the student select as a just general purpose output. Okay, so here, if I've got a master and a student, you got to set the data direction for the master. That's an output. In this case, I made them outputs. That's an output. Mosey, that's an output, master output. And this guy is set to be an input. So you got to set data direction. And the student is exactly the opposite. That's an input. That's an input. That's an input. And no, this one's an output. So you set the data directions appropriate, opposite. Then you set the speed in the master. Don't need to set the speed in the student. It's going to ignore it anyway. Then you set the mode, and these modes better be the same. If they're two microprocessors, the mode's got to be the same. And then you've got to set the master to be true, the master bit to be true, and this one you got to be turned to false. And then you got to turn the systems on, the SPI systems on. And then, of course, if you're going to use interrupts, then you got to put the same, you got to put an interrupt, which level of interrupt you want. And of course, PMIC, turn on that level, and the I bit. And we're going to do a bunch of examples with this coming up. But what if you have multiple students? And so what this shows, if you have multiple students and the master is going to talk to one or the other, then what I've got here, first, again, I can either tie that guy to always be false or high, or I can make it an output. But what I've got here is I have two general purpose IO. And one is connected to this student select, the other to this. So in this case, either they'll both be false, and I'm not talking to either of them, or one will be true and the other false. I have complete control. Now, do you really need two pins here? No. Let's get rid of those. And instead, just use this as an output and maybe use a level shifter, a NOT gate, and to this other one, don't use a NOT gate. Now, one or the other will be one pin, but that pin is already there, the student selected. Okay. Anyway, so I can talk to multiple students, one at a time. Now, again, you can talk to all of them. You can send information from the master to all of them, but only one student output can be active at a time. What else can we do with a SPI device? Well, as I think I said near the beginning of the semester, most small microcontrollers, microprocessors, do not have EBI systems, external buses. Address and data and control bits don't come out. They're all inside. That means you better be happy with the RAM and the ROM and the ports that you have. Except if you got SPI, there's a way to add more memory and more ports. In fact, on your memory base, there is a SPI-driven ROM, which I don't know how big it is. I think it might be a 64K by 8 ROM. I'm not sure exactly how big it is. We're not using it in our labs, but it's on the memory base. But in this case, what I'm going to describe is how to make ports using SPI, extra ports using SPI. Okay, and so we're going to have some examples with this. So here I got really this, I could make this two 8-bit output ports, but really it's a 16-bit output port. I'm going to describe how it works. Now, everything that has to do with serial communication needs shift registers. So here, in addition to the microprocessor, I have two special shift registers. These are both 595s. I don't expect you to know the number or exactly how they work. I'm going to explain how they work. Well, there are two clocks associated with the shift register. Something called a latch clock and a shift clock. The shift clock says, okay, when I get, in this case, a rising edge, each time I get a rising edge, a bit is going to come in. I'm going to read it into the internal device, inside the device. After there are 8 of these clocks, this is an 8-bit shift register, then I've now got 8 bits of data inside the device. And this latch clock says, take those 8 bits and send them to the output pins. That's called the latch clock. So the shift clock and the latch clock, shift clock shifts in 1 bit at a time. Latch clock, when you got all those 8 bits, send them to the output, latch them to the output. Now, there's also here a serial out. Once we have 8 bits inside, when we get a 9th bit, the first bit that came in is going to come out to this one. We get the 10th bit, the second one that was put in this is going to come out. So basically what we've got, we got this system going here. So you put the bits one at a time in here. The first bit that came in will eventually end up here. The second bit that came in will then end up here. And ultimately we have now a 16-bit shift register. Okay, so let's look at the algorithm. Well, first, from the SPI master, well, here I made student select false because it's a master. I set the serial clock to be an output. I set MOSI to be an output. And MISO, I got nothing there. So you set it to be an input, but there's no wire, so I'm not using it. And then I have one GPIO. Now, that GPIO could be the student select if you made it an output. And so this GPIO, what I'm going to do here is, first thing I'm going to do is make this guy high. So this guy here is high. I don't want a clock happening yet. Now, this serial clock is tied straight to this shift clock because guess what? Rising edge here is going to make rising edge here. And so for the mode, I'm going to make sure it's a rising edge that shifts data. In this example, I don't think it matters what the value of the serial clock is before data is transmitted. So it could be high, the default, or low. But so once I wire these things up, I set the data directions properly. All I got to do is write data to the data register for this master. When I write data to the data register, it's automatically going to make 8 clocks. And at those 8 clocks, the MOSI data will eventually come in here. Now I have 8 data bits inside this. But that's not enough. I'm trying to make a 16-bit output pool. And so then I'm going to write 8 more data bits to the master. And at the end of the second 8 data bits, the original 8 values here will be in here, and the second 8-bit values here are in here. So I've got now 16 values. And now this pin here, which is high right now, on the GPIO, I make it go low and then high again. And that rising edge will copy all of these values here and all of these values here. And at the same time, 16 bits come out. That's a port. That's a definition of an output port. And they all have to happen at the same time for it to be called an output port. Okay. And so I've made a 16-bit output port. Of course, I could make it an 8-bit output port just as well. So the cost is very low. I don't need any address decoding. I need a register for each port, a shift register for each port. That's all I need. And turns out I really know pins because I could use the student select for the latch clock. So it's a pretty convenient way to make a couple extra ports. Let's look at an input port. So now, really, this is a 16-bit input port, but it could just as well be an 8-bit input port. So I just use one. This is a different shift register. It's called a 165. It's got 2 clock signals. Again, shift clock, which is just like before, except now it's going to read 1 bit at a time. Serial output is going to come from this to MISO, master in. But here's where the data is going to come in. We're going to read all 16 bits at the same time. What's going to happen is this pin right here, you've got to make a rising edge. that rising edge will copy these 8 pins inside this and these 8 pins inside this. So that's the first thing you do. You make this this GPI open go from high to low to high. So you make that edge. So you copy everything in. Okay, now we're ready to start reading the data into the microprocessor. So again, you set the data directions for all of these appropriate signals. Notice that MOSI, there's nothing connected to it. So now I'm ready to read the first byte because that's what's connected to. Notice here, serial out to this goes to serial into this. So what we've created is a 16-bit shift register. And so now I've got to start the clock running, but nothing comes out. So you write your favorite number to the data register. You write whatever you want, whatever garbage number, or you write 37. You write something to the master, to the data register of this SPI master. When you write that garbage, it's going to start the clock running, and every time one clock edge happens, it's going to read the bit and shift that bit into the microprocessor. After 8 clocks, the value that used to be here is now in here. And the first byte is in the microprocessor, and you store it somewhere. Then you write another byte of garbage, whatever garbage you want, and then the second byte will eventually end up in here as well. And we now have 16-bit input port. Again, if you get rid of one of these, you have an 8-bit input. Didn't require any address decoding, didn't require address bus or data bus. And I have a port. One more example will do. Now, this is 4 8-bit output ports. Now, to do this, I've used a decoder. Hopefully, you remember from 3701 what a decoder is. For this decoder, it's a 2 to 4 decoder. It has 2 inputs. Based on this, if 0, 0 are true and it's enabled, then the 0 output will be true or low. If it's 1, 1, then the 3 output will be true, which is low again. But if this enable is false, then all of these guys will be false high. So that's a decoder. And so first thing for the enable, I have a signal called strobe, and why it's called strobe, it's not really important. These are three just general purpose outputs, whatever you want, that I call them address. It has nothing to do with the address bus. Those addresses are address P0, P1, P2. I want to be able to independently address each of these ports. So I can use 4 different ports, external ports. And this address 00 will be port 0, 11 will be port 3, etc. In strobe, I'm going to use this to make the edges happen exactly where it needs to. So first thing I'll do is put high. So when I put high on strobe, all of these guys are high. And so those are tied to the enables, this latch clock. So this is the same 595 we used for the 16-bit output port a couple slides ago. So all the enables are false. And now what I'm going to do, once I set up the master appropriately, I'm going to just write data to the data register. And that data is going to be shifted into each of these, all 4 of them. Because look at this clock, comes from the serial clock. So it's going to shift into each of these. So all of these will get that data. But I don't want all of those data to go out. So after I've got those 8 data bits inside each of these, I say, hey, which one of these do I want to send the data to? Let's say it was P2. So I have a 10 there. So I write a 10 there, and then this guy that was high, I now make it low. When I make it low, then this pin right here is going to be low. Then I'll make this pin high, and then this will go high. And that's the rising edge I need to have these 8 data bits end up at these pins. And that's all you got to do. And so I made 4 output ports with 4 shift registers and 1 2 to 4 decoder. If you wanted 8 output ports, a 3 to 8 decoder. And I just need one more, I would need one more general purpose IO. So if you needed 128 output ports, it'd be still pretty easy to do, assuming you had a big enough decoder and enough GPIO. Anyways, pretty powerful stuff. Okay, so I'm about to do some examples, and these examples will have, will all have a master talking to a student. And it could be that the master and student are on the same processor. And in fact, the example is going to show it that way. If you want to build it, it's a little, there's one thing you can't do if it's on the same processor that we'll do, but you can imagine these are two different processors. But in any case, I have port C for the master and port D for the student. Okay, so that's what we're going to do with these examples. And so what I'm going to do in this example, I'm just going to take one byte in the master and send it to the student. That's it. And so let's see. Here, that's the data that I want to send out from the master. So I made it as a constant. And this is a variable that I'll get in from the student in a register I'm going to call, or a memory location I'm going to call master in. So we set up the stack as always. Here I'm going to initialize the master. So let's go look at initializing the master. Okay, so first thing I need to do is set the data direction bits. And here I'm showing what the pins are. So that should be an input, an output. This is for the master. That's an output. And we'll set this to be an output as well. So we don't have to worry about it being low. And then I'm going to make MISO an input. And so I've set the data direction this by using direct bits instead of group configurations. Now, notice that I did a dir set and a dir clear here. I'm not changing any of the other bits directions. Maybe the other bits were used for asynchronous serial communication. So dir set and dir clear as opposed to a dir. Okay. And then I got to set the control register. Here, in this case, I'm going to use a clock times 2, prescaler divide by 4. This, by the way, is the fastest speed you can possibly get. And I'm going to turn on the SPI system. I'm going to set the order. I think this will make least significant bit first, make it a master, and I just pick mode 3. That's the control register. And for this guy, for interrupts, I turn interrupts off. Now, maybe you don't even bother with this because there's a default is they're off, but it's good if you ever wanted to change it. You have it done this way. It'd be pretty easy to just say that, change that off to low, MED, or high. Okay, so I've set up the SPI master. And now I just want to point to the output, the data that I want to send out with Z. And so all you got to do, once it's set up, you write to the data register, the SPI data register. Once you write it, the clocks are going to happen. It's immediate. It's just like every other system in the X Mega we've seen so far. EBI, once you set it up, you just store data or you read data. Asynchronous serial, once you set it up, you just write to the data register or you read from the data register. Same here. I just write to the data register. Now, when is it done? Well, you're going to look at a status bit. So this is the status register. I'm waiting for that interrupt flag bit in the status register of SPI. And this is what I did in the example for asynchronous serial communication. I keep in this loop until the bit is set to say I'm done. Now, once it's done, then you know, hey, if 8 bits of data went out, same time 8 bits of data came in, and now I can read the data in the data register, which is not this data, because when I'm reading it, it's what came in to the master input, as opposed to this is the master output. So I read the data that came in, and I store it in master in, and I'm done. Does that make sense? Pretty clean, pretty straightforward. Okay, now let's look at the student side of the same operation. So the master and the student are connected, and now this is the student code, which could be the same processor, but could also be a different processor. And so now I have, this is the data I want to send out of the student, and this is the space for the data that's going to get read in from the student. Set the stack. Now I want to initialize SPI for the student, so let's look at that. Okay, and so here I just wrote those same things. This you're going to see is exactly reversed from the master. So I'm setting these bits as inputs, and MISO is now an output. Okay, and now for the receiver side, I got to turn on the SPI system. I got to use the same mode and the same order of bits. This is what the master had. So I don't need to do anything about the clock times 2 or the prescaler, because the speed is determined by the master. And what else? And I don't want to set this master bit because this is the student. Again, I turn the interrupt off, so there's no interrupts here. So pretty straightforward. And now let's look at the code of the main code. Okay, so here I'm pointing to the data I want to send out. I have it in Z, and I'm going to store that data to the data register. And nothing will happen when you do that. The student will wait. The student doesn't control the clock. So this might be days. The student is waiting for the serial clock to start happening. So here, eventually it'll happen, but until it happens, I'm going to be in this little loop. So again, it might be days. Once you write data to the data register in the master, then the serial clock starts spitting out, and then the bits start getting exchanged. So once the clock starts happening, you'll have the 8 clocks, and once the 8 clocks happen, then this flag will be set, and we'll get out of this loop. Once we get out of the loop, then the 8 data bits are in the SPI data register, the received version of the register, and then I can read that and put it in this variable called student. Now that's swapping 1 byte. What if I wanted to swap multiple bytes? It's not going to change much. So here's a master with, looks like it's got 10 bytes in some table. So I want to send 10 bytes from the master to the student, and from the student to the master. So these are the 10 bytes in the master. And a little trick, I don't know if you've seen this trick before, it's in some of the videos. I may have mentioned it earlier in the semester. Here it's got table, and here is a label called end table with nothing there. If you subtract end table from table, and then you multiply it by 2, because remember, in program memory, it's 2 bytes per address, then you'll know how big the table is. So table size is 2 times that difference. It's a little trick that might be helpful for you. Okay, any case, I now have master input. That's what's going to come in from the student. And so I got the same size as the table, which in this case is 10 bytes. Okay, so everything's the same in the SPI master initialization. But now in the main code here, R17, I'll have the table size of 10. Then I'm going to point to the beginning of the table with Z, and I'll point to the table for what comes in from the student with X. And then here, I'm just going to write the first byte in the table to the data register and increment Z. That's going to start the serial clock running. And here I'll wait till I've finished 8 clocks, till the flag gets set. 8 clocks later, the flag gets set. And now I gotta, in this case, I better clear the flag because I want to run this again. And so clear the flag is in bit 7. And well, I didn't quite clear the flag yet. So here it says, Now take the data that came in and store it where X points. This is the data from the student. And I need to clear the flag. Actually, this will clear the flag. If you read the status register, and then you write to the data register, that clears the flag. Again, what comes naturally. Reading status, writing to data, that clears the flag. Okay, and so this is from the master side. Then here I decremented R17, started at 10, it's now 9, and I run this whole thing again. So this will run 10 times. Once it's run 10 times, then I'm going to get to this endless loop. Let's look at the student swapping bytes. So now again, I have a table. This is the table that I have on the student side. And I'll make the master have these are the variables that'll come in from the student. This initialization for the student is just what it was before. Again, I point to these two tables with X and Z. And then again, from the student point of view, I write data, the first byte in the table, to the data register, but nothing happens. So I go in this loop and I wait for the master to start sending data. Once it's sent 8 data bits, 8 clocks happen, then the value that's come in, I will save to the location that I'm pointing to in RAM of the data that came in from the master. Again, just like before, I decrement this, so I run this whole loop 10 times. So it looks very similar. Now again, I had to clear the flag. And so you clear the flag by reading the status bit and reading the data, same as before. That automatically clears the status. Okay, one more example I want to show you, and that is one program that uses the master and the student in the same process. Now, what I can't show you is a table from the master to the student for various reasons, but I can show you transferring a single byte. So I just copied all the code from one place to the other. So here I've got a place for the master input and the student input, and this is what the master is going to send out and the student's going to send out. And so the initializations are exactly what they were before. I point with Z to the student output, and I write data to the student. And I got to do the student first because the data is in program memory, and there's only one Z. So I read the data that the student's going to send out, and then write it to the data register for the student, and know that nothing's going to be sent out till the master's ready. So now I've got port D student connected to port C master for MOSI and MISO and clock. Okay, and so once I've got the student all ready for data to go out, then I read the value for the master's data, and I send that out. That's going to start the 8 clock times. And this wait loop, I could wait for either the SPI, I can either wait for port C SPI to be done or port D, because they'll be done exactly the same time. Once it's done, I got to clear the flag. Now here I'm reading, I read the SPIC status register, and then I'm reading what's in the data register for port C. So that's going to clear the port C's SPI flag. But I still got to clear the port D flag, and so I got to read the port D status register. And this, otherwise you wouldn't have to do if you didn't want to clear that bit. I can read the SPI data register, but if I don't do this first, it won't clear the flag. Okay, and that's it. So using SPI, and you're going to use SPI in your lab 6. Okay, so in the lab 6 is another one of these 2-week labs. So there's a intermediate submission. And in this this first submission, what you're going to do is you're going to test your SPI system. Let's go find example here. You're going to use your DAD to test the SPI. So you're going to connect your DAD like this shows. There's something called a serial sniffer. on your dad. Did you use that for asynchronous serial? Nobody's making faces like you did, but you can. There's something that'll actually take, you can connect the transmit output and connect it to your dad, and it'll not only, it'll tell you the bytes that were transmitted. You can even tell it parity and all that. Well, we didn't use it here, but we're going to use it. We didn't use it for asynchronous, maybe, I guess, but we'll use it for synchronous. And so what you can do, you can set it as it's shown here. I'm going to use SPI. UART is what we would have used if you used it for your lab. Oh, I guess you haven't had lab 5 yet. That's why. But anyway, this is the serial sniffer. So what we could do is output some data with the SPI and see if from the dad if we did it right. And so that's how you're going to test the SPI output. And then we're going to test the SPI input in a slightly different way by using something called the Who Am I register, which we'll get to a little later. Figure 2. Who Am I register inside your device that we're going to be using. It's called an IMU. In your lab, you're going to use on the robotics backpack, there's a device called an IMU, inertial measurement unit. It's got 3 accelerometers and 3 gyros. So it'll give you linear accelerations in 3 axes and angular accelerations about 3 axes. And that device, that IMU, has a bunch of configuration registers just like your XMega has. And so you can set it up very much like a microprocessor with these configuration registers. And one of them is called Who Am I? And you're going to ask the Who Am I register, which device are you? And there's a couple different IMUs that we've used over the years. Actually, I think 3 so far, and none of the 3 that we've used so far is available today on the company that makes them webpage. And so each one will have a slightly different value in Who Am I register. I think 69, 6A, and the one that's available today is 6B, is the result that comes up. Anyway, Who Am I? We'll talk about that a little bit later. But anyway, for this lab, first part of this lab, you're going to test your SPI system. And by the way, this lab's also the first lab you're going to do in C. Next week's lectures will be all about C. C for the XMega. Okay. Now, something else that I've got while I've got it here. It's a bunch of this green text here. Most of you are going to have, no, this is the one that most of you will have, as opposed to this one. It doesn't really matter which one you have, but when you look at the Who Am I register, you'll know which one you have. And 99%, they're the same. There's this one little difference with the Who Am I register and a couple little other things that really won't be relevant. But I have some header files, which are kind of the equivalent to include for both of these devices. And I want to know if any of you do have this device, tell me, email me. I think you should all have this guy right here. Okay. Anyway, let's go to look at the robotics backpack. So the robotics backpack, this is, now, again, it doesn't matter whether it's this number or the other. The pinout's going to be the same. So this is the IMU pinout. So there's some kind of important things. There is our serial input. By the way, this is a student device. The microprocessor will be the master. So serial in, that's MOSI. And this is MISO, student output. There's the serial clock. And then there's something here called chip select, which has nothing to do with anything, except that for this chip select, we're going to use student select for that. Because the XMega we're going to use as the master, we can use the student select in as an output, general purpose output, and that's what we'll do. Okay. So these are the pins that we got set up. Now this device, in addition to being able to be used as an SPI device, it can also be used as an I2C device, which we're not covering in our course. But it's wired up to be able to done either way. Okay. These are 2 interrupt pins. what we can ask the IMU to do is tell us when it's got some new data. When it has new data, if you set it up properly, either of these interrupts could go low. Now, it goes low because I have set it up to have a default of high. So if the pin goes low, that can trigger on the master on your X Mega, hey, new data, read the new data. Okay, so now where are these pins coming from? This device here, and this one here, these are bidirectional, they're actually analog muxes. You can think of them as switches that have two possibilities. So here, that's serial input, which was MOSI, and there's MOSI. And what is the select line for this analog mux? The select line is this signal right here, which we're going to connect to student select. So this is always going to be, for our purposes, when it's low, then the serial in is connected to MOSI. If this was ever high, then the serial input would be connected to SDA, which again is used in I²C. So we're going to make it low. We're going to make this low so that serial input comes from MOSI. And this analog mux, again, when this guy, student select, is low, then the serial clock will go to the serial clock. And when the serial clock, well, when this guy is a 1, if it ever was, then SCL, again, that's from I²C. But we're going to use the student select for two purposes. And you'll see those other purposes when we get to the rest of it. Okay, and the ports that we're going to use, this is port F. And these are the pins that we're using in port F. So again, that's the student select pin, but we're going to connect it to this, this chip select here for our SPI, for our IMU. And then where's the interrupt? There's the interrupt pins on port C. Now you can use either one. You just got to set it up appropriately for the right one, whichever one you set up to work. So these are already wired up. So port F is what's been wired up. Just like for asynchronous serial, I think we use port D. It's already wired up. Okay, so that is the IMU. Okay, let's go back to the lecture for a second. Let me talk a little off. This has nothing to do with our course, but when you take senior design, capstone design, design 2 has a lot of names. You can, in an alternative to senior design, no matter what degree you're getting, you can take something called IPPD, Integrated Product and Process Design. It's a 2-semester course, fall and spring, and you design something for a company. I've done it, I think, 8 times, once for National Instruments, 6 times for Lockheed Martin, and 1 time for Northrop Grumman. And you get a real product or a real process if you're industrial. Usually they do processes. But anyway, a real product. And the last product I created, or my team created, was what we called MATER, Marine Animal Tracker. We made an electronics box that we cemented to the back of a turtle. And turtles, these kind of turtles are endangered. And so we wanted to get information to try to save the turtles. And we got funded pretty decent money from Northrop Grumman to do this. And so one of the sensors on it was in fact an IMU that we used to use in Micro P, because this was happening right around COVID, and right after COVID, there were no IMUs to be found, not the cheap ones we use. The ones we're using are somewhere between $4 and $12. You couldn't find them anywhere. You couldn't buy them. But out of the box, the company that we get our boards from, he had some old ones from old boards he used to use for our class, and he gave me like 10 of them. In addition to the IMU, we had a light sensor to see how dirty the water was, how much light was coming through. We had a compass, know what direction it was heading. We had GPS. When it surfaced, we could have GPS. We actually had a satellite, so that any time the turtle was above the water long enough time, it would dump all of the data for the last week or whatever to the satellite. it was a pretty cool project. IPPD could be a fantastic thing to do if you get in a good team and a good project. Sometimes the teams, you're going to have other people on your team kind of slackers, and you would then have to make up for them. But here's the deal. Almost everybody that's on an IPPD team, when they finish the project, they get an offer, a job offer. So imagine when you start looking for a job, you've already got one offer in the pocket. And then when you go to your other interviews, you go in with a little confidence. And then you get your second offer, and then you're like a sports star. You can make them bid against each other. NIL money, right? So this company says, we pay $85,000. That's the salary. Well, the other company said 85 too, and say, hey, I already got an offer from another company at that same amount. Can you sweeten it? Well, they might say, I can't give you any more than 85, but how about an extra week vacation? Or how about a signing bonus of $5,000 extra? You have that power if you've already got a job and you're confident. IPPD, I've done it. My teams have all had great experiences. Now, my projects have usually been some of the hardest projects there, but no pain, no gain, sort of like Micro P. Okay, so this is showing what we're going to be doing in our lab. So the XMEG is the master, the IMU is the student. This chip select on the IMU, we're going to connect that, the student select on the XMega. And the interrupt, here I've used port C bit 6. I think that's interrupt 1 as opposed to interrupt 2. These are the analog mux. This is one of the analog muxes, drawn now as a mux. And anyway, so you see what it's all about. Okay, let us look at the manual here for the IMU. So far this semester, all the manuals you've had a look at have been Atmel microchip manuals. This is the one lab you're going to have to look at somebody else's manuals. And remember I told you one of the reasons we use the XMega is because the manuals are really good. And the manual's not nearly as good. And it's going to be a little more complicated to figure out some things, which is why I'm going to give you a lot of pointers about these manuals. It's a pretty big manual. It's, I don't know, 114 pages. There's probably 12 pages you got to look at. And so we're going to talk about some of it. So this is, again, the manual, the LSM DSL. There's another one for the other document. But let's go to figure 3. Okay. So this shows the timing diagram for using the IMU. So first, this is a chip select. We're going to tie this chip select. So this chip select, the SS, the student select, it's going to have multiple purposes. It's going to be used for this chip select here, and also for the analog muxes. And this all going to come from the master's student select output. Okay, this is the serial clock. This is MOSI, and this is MISO. So we can write to the IMU and we can read from the IMU. Okay, so here it tells you what the clock needs to be when we're not sending or receiving data. That's one piece of information we need. The other thing is which edge is the data sampled on for the clock. Another piece of information. So you now know the mode. If you compare these to the equivalent figures in the A331 manual, which is figure 22-2, then you'll be able to figure which mode to use. Okay, now this little dash, this means there's some things not shown. It didn't show all 8 bits. It only showed the first couple bits. So that's some missing information. So between each time you use the IMU, you've got to cycle this chip select. Means go low, and then when you're done, go high. Now, this is not, every SPI system doesn't have this. The IMU has it. Okay, this is for read or write. for the SPI. Let me blow this up a bit. So there's a little bit more detail. So first, look at the first 8 bits. These 8 bits are for very much like the LCD I talked about before, the LCD panel. You can write data to it, you can write commands to it, or you can write or read data from it. Here, this is for read or write. When it's a 1, that's for reading, and when it's a write, it's for writing. Now, these 7 bits, AD, that's address. There are 7 bits for this address. 2 to the 7th is 128. There are 128 configuration registers inside the IMU. And so if we're trying to, let's say, read from a particular register, but if we were trying to read from a particular configuration register, we'll put a 1, and then we'll put that address here. So if you're trying to read from that register, then the data is going to come out, data out. The data will come out the next cycle. So let me put a little line here. So what that means, we're going to read from a particular address. So you specify the address you're trying to read from. And then you do another read. And it knows once it's a read, the next one's going to have to be a read as well, but we'll read the data. This says we're going to read from this configuration register, and then this is the data we're reading. If we're writing, we're going to put a 0 here, and here we put the configuration register. And then we write the data, so this will be ignored, and we write the data. So from the X mega side, from the microprocessor side, we write data, the read or the write, and then we send the data we want to send out for a write, for transmitting. If we want to receive, we say we're going to receive from what configuration register, and then we write garbage out, and so these will be ignored, and the data comes in from there. So again, that place here, that line there, they'll never happen one right after the other. Because once you transmit the 8 data bits, which let's say these guys right here, these 8 bits, then you've got to you see a flag that gets set. Maybe that triggers an interrupt. So some time is going to happen between the end of one cycle of sending 8 bits and then the next 8 bits either being sent or received. And so on your DAD, when you look at this, there's going to be a time space. So this won't look quite like this. There'll be some time between the start of one and the start of the next. Okay, so it's kind of strange. You're writing, and then you're going to write again to that address you're writing, or you're reading, which means you're still writing to this, but then since it's a read, we'll be reading from the IMU. Okay, something under this. This control 3C register, kind of an important register you might want to use. Turns out, and we'll see this in a minute, what we're going to do in the lab, you're going to read the accelerometers, the 3-axis accelerometer. And the data is organized, by the way, this is a 16-bit IMU. So it's going to give for each axis, it's going to give you 16 bits, the low byte and the high byte. And the first 8 bits will be the low part of the X direction. Then the high byte of the X direction. Then the low byte of Y, high byte of Y, low byte of Z, high byte of Z. And these are in sequential order in the configuration registers of the IMU. If you put a 1 in the right bit of this register right here, it's going to make it so it automatically increments those registers. So you don't have to do any extra work. Once you say, I got some new data, you just read in successive addresses, and you'll get all the information. Okay. Let's look for who am I? Who am I? Okay, the who am I register. So this is table 19, and this shows all the configuration registers and their addresses. So this is the address of a who am I, 0F. And if you read the Who Am I register, the value that's going to come up, in this case, that is a 6A. 6A, that's what this particular IMU is going to spit back. I know another one, the 6.9, the one I looked at last night, the one that's now available is 6B. So they keep incrementing every time there's a new one. I think the first one we used was 6.8. Okay, and so Who Am I is a register to see if you're actually doing this process right. So if you can appropriately read from the IMU. Before we're trying to read data, we're just reading the Who Am I register. Let's find here, let's find out X underscore. Okay, so this is the low and high bytes in the X direction. XL here stands for accelerometer. And that's the low byte and high byte, and that's the Y axis, low and high, and Z axis. So these are the things that you're going to read in your lab. By the way, this accelerometer, if you put your board flat on the desk, Z is through the desk, this way. If your board is sitting there and there's nobody walking around or smacking your table, you're going to get an acceleration in the Z direction and none in the X and Y, even though the board's not moving. Why? Come on. Acceleration due to gravity. As Einstein said 100 and some years ago, gravity is indistinguishable between acceleration. And so you'll, in units that you might know, 9.81 meters per second squared is acceleration in the G direction. And you're not going to see that number. You're going to see some number in the Z direction. And you know, if you then take your board and you put it on its side, Z will go to approximately 0, and you'll get something in X. Put it this way, you'll get something in Y. Now, 0 won't be exactly 0 because you know what? The table isn't level. What you've got with your IMU is a leveling device. Once you set it all up, if you want to see if your pictures are level on the wall, you can use it. If you want to see, you want something at 30 degrees, you can use your board, stick it like this. And one of the axes will have the equivalent of 45 degrees, the X and Y might be equal. Anyway. Now, there's some extra credit in this lab. If you use the gyro, angular acceleration, there's a little bit extra credit. If you can use the accelerometer, you can use the gyro. It's nothing different, just different addressing. How fast can this IMU run? Well, it turns out it can run up to 10 megahertz. But you know what? Your X mega can't run that fast. So you need to set the speed so that the data doesn't come out that fast. How fast do you need it? Well, not so fast, because you're not going to look at the data that quickly, but fast enough, less than 10 megahertz. Now, later in the semester, we're going to start running the processor at 32 megahertz, and at that time, we could run it at the fastest speed of 10 megahertz. So every register is described in this section. So it's got some details. So if you wanted to see Who Am I here, you can see it here. It says every piece of information, sort of like in your A331 manual. Now, again, this chip is really cheap. Again, depending on if you buy one or you buy 100 of them, somewhere in the $5 neighborhood, $4 to $15, $14. Now, how are we going to look at the data that comes from this? We're going to use something called serial plot, which you'll be using in Lab 5 as well. But serial plot is something, what you're going to do is you're going to plot the X and the Y and the Z axis acceleration on the screen at some standard rate. So one new point, pretty much as fast as you get the data from the IMU, you'll plot those points. Serial plot is a program that we used to use an equivalent to serial plot inside the Microchip Atmel Studio. But very much like the internal equivalent to PuTTY, it's pretty crappy, the one that's inside. So we're going to use something called serial plot, a program one of the PIs several years ago found, which is good, not great, but it's good enough. And we'll use serial plot to plot those 3 accelerations. And then if you do the extra credit, you'll also plot the angular accelerations on those.